Hello, everybody. This is Aaron Schwartz, one of the secondary math specialists with Montgomery County Public Schools. Today's video is called Hanging in the Balance. It's about single variable inequalities. In Unit 1, Topic 2 of the current Algebra 1 curriculum, the students learn to write, interpret, and solve inequalities to express relative values. The key ideas include that inequalities represent a constraint, and a variable inequality has an infinite number of solutions. Some of the helpful skills that students have learned include that inequalities compare values. This actually starts in elementary school as early as first grade, when students start to compare numbers such as 4 is greater than 2 or 2 is less than 5. And they start to write these inequality statements near the end of first grade. Inequalities represent a constraint, and a variable inequality has an infinite number of solutions. As early as sixth grade, students start to solve single variable inequalities that involve one step of algebraic manipulation. Solving and graphing linear inequalities in the form p times x plus q is greater than r is done in seventh grade and in IM. At this point, students start to solve algebraically and graph the solution sets. Many students get to Algebra 1 and they really struggle with inequalities. This is because it's a very difficult concept. The idea that you have a range of answers as opposed to one answer can be very challenging to a lot of students. So even though they've been exposed to inequalities as early as first grade, they may still have some areas where we need to remediate or to help them better conceptualize the content. And one of the best ways to do this is with the image of the hanger on the right of the screen. What we would do is give this hanger and this image to students and ask them what they notice. One of the first things that they're going to notice is that it's out of balance and that the right side weighs more. It seems like a very obvious thing to say, but it's actually the most important place to start. Some students may then focus on the fact that there are more green circles on the right, but more pentagons on the left. Now, some students are going to be able to immediately conclude that the circle weighs more, and that's great, but we want to refine their notices so that we can better validate that statement. So the next thing we might ask students about is, what if we remove two pentagons from each side? Or some students may even say you can remove two pentagons from each side without changing the overall balance. From there, some students may notice that we can remove a circle from one side without changing the overall balance. And now a student can most confidently say a circle weighs more than a pentagon. They may have been able to say it before, but now they can validate that with actual explanations. Now, this is really great in terms of developing the conceptual understanding, but we need to make the bridge to the algebraic manipulation. So we're going to do the same activity again, but it's going to be, what do you notice now? And we've replaced the pentagons with an actual unit of mass. So in this case, we're going to say that the pentagons weigh a gram or a pound or whatever it is that they weigh, but they weigh 1 unit. Some students may notice that there are more green circles on the right, but more pentagons on the left. This is an algebraic inequality as an equivalent. We can say that one circle and a mass of 3 weighs less than two circles and a mass of 2, or 1c plus 3 is less than 2c plus 2. Previously, students may have noticed that we can remove two pentagons from each side. This has an algebraic analogy. We can subtract 2 from each side, and we have that a circle and a mass of 1 weigh less than 2 circles. Previously, students said we can remove 1 circle from each side, and again, there's an algebraic equivalent. 1 is less than a circle, because we've removed 1 circle from each side. Where students previously said a circle weighs more than a pentagon, they can now say a circle weighs more than one, or one weighs less than the mass of a circle. What are some of the possible weights of a circle? Well, this is a really interesting question to pose to students. And one of the best ways to do this is either to have a poster in the back of the classroom that has a number line and give students those sticky dots to put their response up on that number line. And each student gets 1 dot or 2 dots or 3 dots, and they have to put those dots in various places to answer this question. Another possibility is to use Desmos and the activity builder, and I'll build a link into the MCPS classroom for that. And so students may generate a number line that looks like this. And we have a bunch of numbers here. Students have picked a bunch of different places, but there are now some really good questions we can start asking students. For example, why didn't anybody include 1? Well, they say that a circle must be more than 1. So it doesn't matter how much more, but it's got to be something more than 1. So students didn't include 1 because it's not equal to 1. The graph above used 13 dots, or in your classroom it might use 30 dots. What would this look like if we used 100 dots, or 1,000, or 10,000? And we'd want to hear students say things like, the points would look like a line. The points would become so indistinguishable that it would be a line. We wouldn't be able to fit all the dots in because they'd be overlapping. Whatever it is that gets them to express this idea of a continuous line that starts somewhere after 1, that's what's important, because now they're going to perceive the graph differently. In fact, it's now going to shape how they view how the graph above and how the dots make sense of this graph. Now that line no longer represents some arbitrary rule, shade right or shade left. Now it represents the collection of all of the possible dots that we could include. The dots are so stacked together that they are indistinguishable. There's an infinite number of them. And so now the graph no longer is a step in the solution process. Now the graph is about conveying the meaning of our algebraic representation. It's showing all of the dots that are greater than 1, all of the dots that make that hanger balance the way it was. And now we can start asking them, well, why is it that you didn't include this 1? Why is it that you have this so-called open dot? And students can say, well, the 1 wasn't actually included in our set of values. All of this changes the way we view the graph, and it's no longer about open dot, closed dot, right or left, these arbitrary rules, because now it's a communication tool. And we can ask them, what does the open dot communicate? It communicates the boundary. It communicates the value that's not included. And what do the values to the right or to the left of the dot mean? Well, they mean the numbers that are greater than that value or less than that value. And so students should now be able to graph an inequality in the form x is greater than 1 just as easily as x is less than 1, because left or right are no longer arbitrary steps to follow. We're concerned with which set of values satisfies the inequality. Are we looking for numbers that are more than 1 or numbers that are less than 1? It's very common that some teachers who don't really have that firm understanding developed in their students may just say, well, always put the variable on the left side, and then always put the variable on the right side and then follow the arrow or whatever mnemonic it is. But that doesn't really get at the conceptual understanding of the content. And by teaching it this way, students don't need to worry about which way the inequality points to draw their line. They understand what they're trying to represent with the graph. So we also want to develop some aspects of the algebraic manipulation. So we're going to go from concept to procedure again here. This is an activity that's done in the Math 7 and IM curriculums, but it's a really important task that's based on understanding why you have to so-called flip the inequality. For this, we're going to start out with a base inequality. We have a table, and what we're going to ask students to do is to perform each of these operations with the inequalities as they are, and then ask them whether the inequality that results is still true or if it becomes false. This can be done as a sequence of steps, or it can be done as replicating each step from scratch each time. For this video, I'm doing a series of steps. So step 1, we're going to add 6. And yes, 42 is greater than negative 18. That's true. I'm going to subtract 12. And 30 is greater than negative 30. That's still true. I'm going to multiply by 2. 60 is greater than negative 60. That's still true. Now, I might divide. I may tell students to multiply by a fraction at some point in here. It doesn't matter. That's a judgment for your own class, but you want to include the operations of addition, subtraction, multiplication, and division, or multiplication of fractions somehow. And so when I divide by 3, I get 20 is greater than negative 20, and that's still true. And now I'm going to multiply by negative 1. And negative 20 is greater than 20. That is actually false, and that's the first time I've come up with a false statement. And so now we want to go to that procedural part. For what operations was the result true? And we want students to tell us that all except multiplying by a negative. And what implication does this have for solving inequalities algebraically? And what we want students to tell us is that whenever we multiply or divide by negatives, we're going to need to reverse the direction of the inequality sign. Otherwise, our inequality is no longer true. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below.